April 8, 1943, North Atlantic, midnight. A convoy of 40 merchant ships limps through 30-foot swells. U-boats circle beneath the waves like wolves. Another freighter explodes, the third one tonight. The captain knows they're all going to die, except one man sitting in a London office 3,000 miles away refuses to accept it. Patrick Blackett had no naval command, just a notebook full of equations that admirals called worthless. His colleagues thought he was insane, but what he calculated in that cramped office would turn the entire Battle of the Atlantic on its head. One physicist, one impossible formula, and a discovery so revolutionary that U-boat commanders couldn't believe what they were seeing. This is the story they don't teach in history class, the story of how a civilian with a pencil saved more sailors than any battleship ever could. Stay until the end, because what the math revealed shocked everyone, including the Germans. April 8, 1943, North Atlantic, midnight. Rain lashed against the bridge windows of HMS Violet as the corvette heaved through 30-foot swells. Searchlights cut through the darkness, chasing the ghostly outlines of Allied merchant ships struggling to maintain formation. Somewhere out there, beneath those black, moonless waters, the German U-boats were waiting, silent predators with torpedoes aimed squarely at the heart of the convoy. Lieutenant Commander James Fenton gripped the railing and stared into the storm. Every few minutes, a flash of lightning illuminated the faces of his men, young, pale, exhausted sailors who knew they might not live to dawn. The convoy's wireless crackled with grim reports. Another freighter struck, another plume of oil and flame on the horizon. For months, the same story played out again and again. Merchant convoys carrying food, ammunition, and steel to Britain were being hunted down faster than the Allies could replace them. German Admiral Karl Dönitz's wolf packs roamed the Atlantic in growing numbers, sleek, coordinated, and devastatingly effective. By 1942, the Allies were losing nearly 700,000 tons of shipping every single month. If the convoys failed, Britain would starve. Inside the Admiralty War Room in London, the situation seemed hopeless. Charts pinned with red pins mapped an ocean of loss. Every decision, how to route convoys, where to place escorts, when to sail, felt like guessing in the dark. The Navy fought with courage, yet nothing seemed to stop the invisible killers beneath the waves. And that is where one unlikely man entered the story. Not a sailor, not an admiral, but a scientist, a Nobel-winning physicist named Patrick Blackett, a man who had once studied cosmic rays and atomic particles. He was about to turn the Battle of the Atlantic on its head with something no one expected: math. At the time, most in the Royal Navy viewed Blackett's presence with mild amusement. What could a civilian, buried in equations and probability charts, possibly teach hardened sailors about war? But Blackett wasn't deterred. He refused to accept that war at sea was ruled by luck. To him, every action, from the spacing of ships to the timing of escort sweeps, was measurable, predictable, and optimizable. With a small team of statisticians, Blackett began poring over convoy reports, attack logs, and escort patterns. They treated every recorded U-boat encounter as data, decoding the chaos of battle into ordered numbers and probability curves. Slowly, patterns began to emerge where commanders had only seen randomness. In corridors lined with maps and ticker tapes, Blackett's operational research section started asking questions no one had dared to ask. Why were convoys with more ships often safer than small ones, even though logic said bigger groups should make bigger targets? Why did more escort ships not always translate to more protection? Why did U-boats strike at particular angles and not others? Blackett's conclusions would shatter the Navy's assumptions and change the tide of the war. The first time Patrick Blackett walked into the Admiralty War Room, the senior officers barely looked up. A tall man with a calm demeanor and the kind of eyes that never stopped calculating, he carried no swagger, no medals, just graphs and tables under his arm. He took a seat beside a plotting chart showing convoy routes and politely asked to see the raw data on ship losses. The admirals exchanged glances, unsure whether to laugh. O Convoy HX-229 steamed westward in brutal weather. Sheets of rain battered the hulls, and the wind screamed across antennas and rigging. The German wolf packs closed in again. Dozens of submarines, their periscopes cutting like knives through the night. But this time, the hunters met a very different prey. R take offense. Blackett didn't care. He had fought in the First World War as a naval gunner. He had seen what happened when good men fought blind. Now he intended to ensure that science, not luck, guided every decision. For weeks, his small team, nicknamed Blackett's Circus for its mix of scientists, statisticians, and even zoologists, worked around the clock. Their office was cluttered with coffee cups, sea charts, and reams of interception reports from the Atlantic. Every ship attacked, every depth charge dropped, every sonar contact made, Blackett turned it all into numbers. Patterns began to reveal hidden truths. One of the first shockers was convoy size. Naval doctrine said smaller convoys were harder for U-boats to detect. But the data told a different story. Large convoys, those with 40, 50, or even 70 ships, were actually safer. The math explained why. A convoy was only as visible as its outermost edge. 10 ships or 70, the footprint wasn't that different on sonar or periscope. But the larger the convoy, the fewer escorts needed per ship. The enemy's torpedoes could sink several targets in one attack, yet they simply couldn't strike them all. A U-boat closing in on a huge convoy faced overlapping sonar sweeps and counterattacks. Statistically, it died faster than it could hunt. Then came the matter of escorts and depth charges. Commanders believed that hurling hundreds of depth charges at suspected contacts increased the odds of sinking a submarine. Blackett's analysis crushed that belief. His team proved that the probability of hitting a submerged U-boat did not rise proportionally with the volume of explosives. It depended more on precision, not panic. Carefully timed salvos, launched with accurate sonar fixes, were far deadlier than random barrages. He also calculated the most effective spacing between convoy ships, a balance between visibility, maneuverability, and protection. Too close, and ships risked collision in rough seas. Too far, and escorts couldn't react fast enough to threats. Through endless iterations, the math revealed the sweet spot, roughly 1,000 yards between vessels, close enough to share radar sweeps but wide enough to avoid catastrophe. His findings reached the Admiralty in a formal report that some officers dismissed as academic fantasy. One vice admiral smirked, saying, "We're fighting with ships, not equations." But the commander-in-chief of Western approaches, Admiral Sir Max Horton, was different. Horton had seen enough blood to know that if data could give his captains even a fraction more time to react, it was worth trying. He authorized Blackett's recommendations to be tested in real convoys. The orders went out quietly across the Atlantic bases. New spacing protocols, revised escort patterns, and disciplined depth charge attacks. No grand announcement, no fanfare. Just spreadsheets quietly turning into survival. Weeks later, the results were impossible to ignore. Convoys, once losing 5 or 6 ships, were arriving nearly intact. Escorts were reporting record numbers of confirmed U-boat kills. In the operations room, red pins marking losses began to thin out. The seas that once seemed cursed with invisible predators were starting to yield to logic. The men on the escorts never met Patrick Blackett. They didn't know about his calculations or graphs. But when an incoming torpedo missed by a hair, or when sonar guided them perfectly onto a kill, they were living proof of his work. In the war for Britain's lifeline, science had found its voice, and it spoke in the language of probability. March 1943, mid-Atlantic. The merchant ships sailed in tighter formation, their spacing precise as if laid out on graph paper. The escort corvettes and destroyers held disciplined patrol patterns instead of erratic sweeps. Radar operators monitored air gaps while sonar pings painted clearer, more predictive contact maps. Every move, every turn, every depth charge had been calculated with the methods born in Patrick Blackett's cramped London office. At 2:17 a.m., a periscope breached. The U-boat commander, Kapitän Lieutenant Hans Günther Lange, saw what looked like the start of an easy kill. The convoy stretched across the horizon, dozens of silhouettes. He gave the order to fire, but as his torpedoes hissed into the water, the escort ships reacted instantly. Sonar plots triangulated their source within seconds. Instead of scattering, the convoy maintained its formation. HMS Violet and the destroyer. Havelock converged from two vectors, launching just 4 depth charges, each precisely timed. The ocean exploded. A column of water rose hundreds of feet, then silence, followed by a blast of oil and debris surfacing through the rain. Lange's U-boat was gone. Another wolf fell to the hunters that night. Across the Atlantic, similar encounters were repeating. Convoys that had once been helpless prey were suddenly beating back the pack. The numbers were staggering. By the end of 1943, Allied shipping losses had plunged by more than 70%. U-boat sinkings skyrocketed. The balance of power in the Atlantic had shifted, driven not by new weapons or massive fleets, but by mathematics. In the war rooms, the mood changed. Commanders who once dismissed Blackett as a dreamer now quoted his analyses in tactical briefings. The phrase operations research began to spread through Allied planning like wildfire, from anti-aircraft gun placement to bombing strategies and radar sweeps. For Blackett, the recognition was bittersweet. He had always resisted the word genius. To him, the real triumph was proving that war could be fought intelligently, that courage could stand beside calculation. When asked how he found patterns in chaos, he reportedly said, "We stopped guessing. We started measuring." By early 1944, Dönitz knew the truth. German intercepts revealed convoys slipping through his patrol lines untouched, while his own fleet dwindled under relentless counterattacks. He pleaded for more advanced radar and faster submarines, but time had run out. The mathematical tide could not be reversed. In London, the Admiralty quietly expanded Blackett's program. New analysts poured in, scientists, engineers, even psychologists, turning statistics into survival strategies. What had begun as a desperate experiment now became one of the war's most decisive intellectual victories. The Battle of the Atlantic was far from over, but its fate had been sealed not on deck or in the depths, but in a room full of equations where a civilian dared to believe that reason could outthink terror. The convoys rolled on under the gray Atlantic sky, guided by unseen geometry, guarded by invisible logic. The world would later remember radar, the Enigma codebreakers, and the D-Day landings. But the quiet revolution of Patrick Blackett's impossible calculation ensured those victories could even reach their shores. May 1945, Liverpool docks. The war in Europe was over. The Atlantic finally lay quiet. Rust-streaked merchant vessels rolled gently in the harbor, their cargo holds full instead of empty, their decks scarred from years of hard duty. Sailors disembarked in silence, some laughing, some crying, all worn thin by years of fear and endurance. Among them were men who never knew the name Patrick Blackett, yet whose survival had been shaped by his unseen hand. In a modest office near Whitehall, that same hand scribbled one last equation in a notebook. Blackett leaned back, exhausted but satisfied. The world's greatest navy had learned to think like a scientist, and because of it, Britain still stood. The Admiralty's final report on the Battle of the Atlantic was brief but telling. "Sinkings are now rare," it read. "Convoy system effective." There were no medals for mathematicians, no grand parades for physicists. The victory had come quietly, in pencil lines, probability charts, and equations written by lamplight. But inside those numbers lived thousands of saved lives. Blackett later remarked that his methods had shown something profound. Modern warfare was as much a problem of information as it was of firepower. Somewhere between the courage of sailors and the cold calculations of science lay the key to survival. He proved that intellect could be as lethal as any weapon if aimed precisely enough. By 1948, he would receive the Nobel Prize, not for his war work, but for his studies of cosmic rays and atomic physics. Yet among those who knew the secret story, his greatest experiment wasn't in a laboratory, but on the Atlantic. His operational research was adopted across the world by militaries, industries, and governments as the foundation of decision science. Decades later, when historians examined the metrics of the Battle of the Atlantic, they found an inflection point. a moment when loss rates plummeted almost overnight. That was the moment math entered combat. It remains one of the clearest examples in history that reason, discipline, and data can accomplish what brute force cannot. The rain that once swallowed ships now fell softly over the docks. Somewhere in the distance, the faint whistle of a freighter echoed across the Mersey. Supplies still moved, commerce still flowed, an echo of those desperate convoys that had once been the lifeline of the free world. Patrick Blackett never sailed into battle again, but his calculation, his impossible model, still sailed on every safe crossing that followed.